What number do you start with without two?
Oops. Oh, I'm not even doing this. 6. What is this? 6 SI.
Yeah.
Maybe I should put on some glasses.
Well, not anymore.
That helps. Can't see.
Oh, I thought we were talking about what's money on the
She was a Google cow. She was
All right, let's keep it down to low roar, please. Somebody like me might be trying to figure something out. CA?
Oh, I think so now.
Yeah, her own solo career. Like Will I Am had black actors in it.
like 2 years ago or something, they were like, Black Eyed Peas officially disbanded, and they like haven't made music in like 10 years.
Yeah.
It just now. That's
All right, so okay, if we can drop the piece, the peas, we can stop with the peas. The peas. So we're going to start with calcium phosphate, right? +2, calcium, second column metal, always going to be +2. There's 3 of them, right? 3 +2s. Ca, Ca, Ca. So +6 total. Phosphate, PO4, 3 minus. There's 2 of those. So we know we have a balanced compound. All right. We already know that calcium's 1 element. The oxidation number is +2. The overall, this is a 3 minus, right? So oxygen's always -2, yes? Unless it's with peroxide. So -2, 4 times, 0, 0, 0, 0, 2 minus, 2 minus, 2 minus, 2 minus, 8 minus, yeah? How many phosphorus? 1. So 8 minus what is -3, and that would be a plus, -8 + 5, right? So phosphorus is +5. And again, in phosphate, phosphorus is always going to be +5. So if you're not one of those people that likes to count on your fingers and toes, then you can just memorize phosphate, phosphorus is 5. So those are the oxidation states for calcium phosphate. O2 in this case is not a peroxide, so that's -2 twice, -4. And to bounce it up 8. So there's 1 silicone to spread that charge over, so silicone's +4. Okay? 10 carbon solids. Carbon, apparently that's a natural occurring state, so 0. Come over here, calcium, 2+. Oxygen, 6 minus, right? Yeah. 6 minus because there's 3 O2s. Right? So 6 minus, there's 1 silicone. Yeah?
Yes.
Right, but the overall, remember, this has to be 2 minus to make the compound neutral. So 4+. Yeah? Did you see how I did that? So we had 6 minus overall, but it's in a compound. So this anion silicone oxalate or silicate is SiO3. Right? So this SiO3 has to be 2 minus to charge balance the calcium, which means that we have 2 left over. That gives us a +4. Phosphorus, 0. Okay, oxygen 2 minus, carbon 2+. And is that all we need for that? No. There's another step, correct? Oxidation and reduction. We've got to figure out which one's which. Okay, so calcium's 2+, calcium's 2+, no change there. Silicon's 4+, silicon's 4+, no change there. O2 is 2 minus, no change there. No change here, no change there. carbon is 0, carbon is 2 plus. So carbon goes from charge state of 0, oxidation number of 0, to 2 plus. And then phosphorus goes from plus 5 to 0. All right? To get to 0, you have to add electrons. Like, so if we were to balance this, we'd have to add 5 electrons for each phosphorus. So we'd add that to go to 0. And this one, we'd add 2 electrons here. So that's what we're looking at for our half reactions. We would still have to follow through to get the complete reaction like we're going to do in the next problem. Okay? So that's what I expect you to do, maybe not quite that fast. Yeah, Adrian.
Can I get a nice?
Oh, yeah, of course.
Thank you.
Yep. Any question on that?
So carbon reduces phosphorus oxide.
Nope.
No? I picked it again?
Yep.
Yep. I'm gonna have to watch that.
Yep. You know, Leo goes Gur or whatever. Right, that's what I would use. I just loses electrons. But how do you know if it loses electrons? Because the oxidation number goes up. Gain electrons reduced, right?
Can you explain how you got a +2 for calcium and not the +6?
Because,
Is it because there's 3 of them?
yeah, each one's 3 and then there's +6.
So overall it would be +2. And then,
But each calcium's +2.
yeah. Okay.
They're all the same oxidation state. We're spreading +6 charge over 3 calciums. So each calcium's 2 plus. We have 2 phosphates and 3 minus, so 6 minus. Charge balance it with 3 2 pluses.
Okay.
And calcium's great because we don't have to figure out what it is. It's going to be 2 plus,
Okay.
unless it's elemental calcium.
Cool.
Yeah. Marlene, you good?
Yeah.
Okay. Araceli, you good? Okay. Okay. What about you, Jennifer? You're giggling over there. Does that mean you know it or you don't know it? What? Yeah. Thumbs up. Feel like we're texting now. Thumbs up. Okay. No, we're not. I didn't say that. Anyway. Okay. Do we want to see another one
Yeah, why not?
Yes.
of this type or from the quiz?
Same type.
Same type. Okay.
Maybe C.
Maybe C.
All the above. Keep going.
All right, I'm not going to change colors this time. I was way too much room for my little brain. 2 H. Oh, it's because it has all the 2's in it, huh?
Yes.
H2O2. That's so mean. All right. Right. All I hope is if I do get an interview and for the full-time position, that I don't have to write any 2's on the board.
Yeah.
Just I'll be cut right there. It's like, do your favorite lecture. No 2's. Go fish. All right. So solid.
Not really.
You will be a ton here once you get set for a while.
Why do I take them off? I don't know. Apparently I'm going to need glasses all the time now.
Welcome to my life.
Leave us.
All right. So here we go. And we just spent an hour on this, by the way. And these are 20-minute quizzes. So I'm just saying. You might want to do them over and over and over again until you can do them a little bit faster.
Yeah,
And that's so that's what I always suggest, right?
just drill them.
Drill them. Take them like an exercise or a drill. A drill is the perfect way. Once you know how to do it again, do it again, do it again, do it again. then try to do it without looking. If you can't do it without looking, do it again, do it again, do it again. Because the problems have the same pattern all the time. All we're doing is changing the numbers. That's really all we're really doing. There's like 5 different types of problems. So if you can break it down that way, maybe I should break it down that way next time I do this, if I ever do it again. I will break it down in a different way, thanks to you guys. So there you go. Part of an ongoing experiment of insanity. So here we have H2O2. This O2, because there's only 2 H's, H takes precedence, so it's +1. So each oxygen is -1. Uh-oh. Metal and hydrogen. Metal, right, from the left side of the periodic table, hydrogen, -1, +2. Hydrogen, in elemental form, 0. Beryllium, 2+. Oxygen, 2-. Hydrogen, +1. Oxygen, 2-. Oxygen gas, 0. So oxygen goes from -1 +1 electron to -2. Right? And that oxygen also goes from -1 to 0. Well, yeah, whatever. Goes to 0. That's the oxidation number, not oxygen. +1 electron. Right? Did I do that right?
Sorry.
Yeah. Ooh, is there chimes?
I'm
Is there
sorry.
wind? Is it cooling off? Is it cooling off, everyone? It's cooling off period. All right, so what else do we have? So oxygen is both what? Reduced and oxidized in this equation. What else? Hydrogen is -1. So hydrogen, this is oxygen. -1 and +1 and 0. So hydrogen as well. Hydrogen goes from -1 to 0, which is +1 electron, and then goes from +1, if you want, to that's it, to 0 as well. So to do that, you have to add 1 here. So hydrogen is also oxidized and reduced. So hydrogen is an oxidizing agent and a reducing agent. Oxygen is an oxidizing agent and a reducing agent in the same equation, which is what makes peroxide so unstable, right? If you can go either direction, you're not stable. Some of us seem volatile, but we're actually very stable. Some of us seem stable, but we're very volatile. Peroxide is what it seems, unstable. All right, so any question on that one? No?
Still writing it down.
So it's amazing how many shows, like before 2015, are about pathogens being released that cause a pandemic. It's almost like they advertised it. And I read a book by the guy Dan Brown. If you ever get a chance and you want to read some fascinating symbology, read Dan Brown. Angels and Demons. This one there's another one that's about the contagion, but it's called something else. But yeah, and the famous one with Tom Hanks.
That one's Angels and Demons.
No, there's another one though. Even better. Yeah, Da Vinci Code.
And then there's a third one. Something about fire or something.
Right, Inferno. That's about a contagion that's released, and it's a DNA manipulation to defertilize the population. and it came out in 2015. Just saying. Right, so if you look at iron, it's on the reactant side, it's 2 plus, and then on the other side, it's 3 plus. Some electronic configuration changed, so it's going to be oxidation reduction.
Okay.
That's how you can really tell.
Okay.
And since it's an increasing number, you know that iron's going to be oxidized. But let's break it up into half reactions. What are the half reactions? That's the part that just looks at one of them. This happens every single time. Oh, now you have that I thing going on. So Fe2 plus goes to Fe3 plus. So if we're at one state, 2 plus, and we lose an electron, the electron goes on the product side. Yeah? Okay. Then, are we balanced? We're not balanced yet. Oh yeah. Well, let's write down the other one. And then, what was that?
Cursive?
That's cursive. That's a kindergartner. It's my inner kindergartner. Get in touch with your inner kindergartner. MnO4 goes to Mn2 plus. So that's what we have so far. Let's go up here and check oxidation states. I always like to do that first. So here we have oxygen 4 times. Oh, 2 minus 1, 2 minus 2, 6, 8. But we have an overall 1 minus, so we have to get minus 1. That makes this plus 7. So manganese is plus 7. And so in permanganate, manganese is always plus 7. In phosphate, phosphate's always plus 5. Right? And if you say it along with me, you're drilling. And if you're drilling, you're not learning, memorizing. But if you're memorizing, you're putting it in your memory bank. And sometimes you can access that during times of stress. Go ahead.
So is
like a test.
manganese always a plus 7, but when it's attached to an oxygen, or
No.
it's just always plus 7?
No, always in permanganate.
Always in manganese is a plus 7. In this
Right.
situation.
In
Got
this,
it.
so if you see permanganate, you can say it's plus 7. If you see phosphate, you can say phosphate's plus 5. Phosphorus is plus 5 in phosphate.
Okay.
But we already know manganese doesn't have to be 7. It can be plus 2. It has a variable charge based on what it's connected to or what we say the ion charge is. So this has 2 less electrons than protons. This has 7 less electrons. So we have to move 7 electrons there. Go ahead.
So why does it go from from 2 plus to 3 plus? Like,
Why does this one go from 2 plus to 3 plus?
yeah. Like,
Because it had 2 less electrons than protons, and now it has 3
That's
less.
what we're figuring out.
Yeah, we don't know why. We still don't really know why. It's just the way the electrons move, right? Based on the pattern of energy that we have and where the electrons are in the element itself. So with iron,
So iron is always like 2 plus or?
not always anything.
Oh, okay.
Its favorite states are 2 plus and 3 plus. And it's a metal, and metals tend to lose electrons, and especially at our level. At our level, that's all they do, is lose electrons. Okay. If you happen to stay with chemistry. So my favorite thing that people say to me when I was just first done, and I got my doctorate, and I was hot stuff, or I thought I was, turns out I wasn't, but I thought I was, which was all that counted to me. And then they would say things like, oh, I had chemistry once in high school. And I go, yeah, I know. It took me 7 years to do what you did in a semester. All right. So I've always been like that, which is why I'm here. So MnO4 minus Fe2 plus. So we have 1 electron here, and then, we have to add 5 electrons here. Now, what do we do next? So what are the rules?
You have to add more O's, you have to add H2O.
Oh, so do we do that? Are we doing that up here, or do we do it down here, right? Down here. Right, in the half reaction, we have oxygen here. We can't have oxygen on one side and no oxygen on the other. So we have to add, what do we add? Waters. Right, so now we have H2O. How many O's do we have? 4. So we have to add 4 waters. remember, we can't break up any compound that we have. We can't just put a 4 in here. We have to put it up front. Now we have how many hydrogens? So we have 8 hydrogens on this side, but we don't have any on this side, so we have to add 8 hydrogens. All right, so we're getting there. Now, we need to balance out what now? Yeah, the next step is electrons. We're still an acid, right? We're still pretending we're an acid, but we have to do this in base. So there's another step after we finish it. Let's make this a little more legible. Well, at least in my mind, it's more legible. All right? So we have 5 electrons here. How many do we have here? 1. So we have to multiply this whole thing by 5. 5 times this whole equation, and I'll move it down now. So 5 Fe2 plus yields 5 Fe3 plus 5 electrons. All right, so if we were doing this in acid, right, that it's okay to have free hydrogens. Because hydrogen is an acid. A proton is an acid. So we have free protons floating in here. It's an acidic solution. But we don't want an acidic solution. We want a basic solution. So what we want is, instead of more H plus, we want more OH minus. So in order to add OH minus, to make water, we add 8 OH minus to this side, and to this side too. 8 OH minus. Is that right?
Yep.
Yeah, that's right. So now everything's balanced, except for what happened. This is actually 8H2O, right? Because H plus and OH minus go together to form water, right? All right, so H2O. So cancel those out. And we look at the whole equation, but what happens? We have 8H2O on this side and 4H2O on that side. We don't want that. So we combine them. And that's one way you can tell. The water's going to be on the reactant side in a basic solution. Because we're going to have OH minus left, and I didn't draw that side. So we're going to say 4H2O. Now we're just going to sum it up. Plus MnO4 minus plus no E's. Oh, but there's one more thing. And use your fingers because you're like a child. 5 Fe2 plus. Now where are we? Oh, right, other side. So Fe 5 Fe3 plus Mn2 plus 8 OH minus. And there we go. That's all there is to it. 8 steps. Or so. Seemed like only 8 to me. Right, so let's go through it one more time, right? We start off with permanganate, which has manganese in it. Manganese in permanganate is a +7. We get +7 because we have 4 oxygens at -2. That gives us a -8 charge overall. However, there's a minus here, so we have to retain 1 more electron than we do proton. So what we end up with is -8, leaving the -1 is +7. So manganese is +7. Then we add iron at 2 plus. Keep track of the oxidation states. So let's just put 2 minus here. And then 2 plus here, so just a 2 here. We come to this side, manganese is 2 plus, which is much different than 7 plus, right? It's a 5 electron difference. Plus Fe3 plus, which is a 1 electron deficit going from product, or reactant to product. Now, the second step is to break it up into half reactions. We group the similar reactant. So iron goes from 2 plus to 3 plus. plus an electron. Remember, when you're losing an electron, it goes on the product side. When you're gaining an electron, it goes on the reactant side, right? We're adding an electron to something that exists. So we go to manganese, permanganate, and manganese containing compound, and we say, oh, that's -1. To get to +2, to get from manganese 7 to manganese +2, we add 5 electrons, right? And since we're adding electrons, they go on the reactant side, and we end up with Mn2+. So those are our two half reactions. Now, in order to balance, and let's just do it again, right? So that you don't have to rewind. You guys may have the blue, but I don't have the blue. All right, so these are our half reactions. All right. We have 5 electrons here, Mn2+, great. That gets us there, but we have these oxygens. When we have oxygens, the only way to balance them is with water. So we add 4H2O because there are 4 oxygens. Yeah, 4 oxygens. But now we have what? Hydrogen left over that we have on this side that we don't have on that side. It's all about balancing. You don't want to just hop on one leg all the time unless you have to. So we balance it out and we put what? 8H+. Okay? That doesn't change anything with this one because this one is balanced, right? But we don't want electrons left over. This is what we call charge balancing. We have to have the same amount of electrons move from reactant to product. From reactant to product. So we have 5 here, so we need 5 here. So we multiply the entire half reaction by the number of electrons we want to end up with, which is 5. So let's bring that down, and we'll just do 5 Fe2+ goes to 5 Fe3+. And in this particular reaction, this is easy, right? We don't have to worry about anything. Now, this is great. If we were doing acids, we'd be finished. But we're not. We're going to do it in basic solution. So we're going to control the pH. That's what we talk about acid-base. If it's just neutral, it's pH 7, which means there's just as many hydrogens plus as OH minus. The concentration is exactly the same. Here the concentration isn't the same. It's in acid. We're going to make it in base. And how do we do that? By adding base. What is base? Often OH minus. So we have 8 hydrogens that are unaccounted for. If we have extra OH, we're going to use up all the H+. We're going to use up all the acid and have leftover base. So 8 OH. All right? But we can't just add it to one side. We can't just add something to one side. It's not fair. It's not equitable. So we're going to add it over here too. All right. Now we have to remember that H+ plus OH minus, this formula here, is water. So we have 8H and 8OH, and we're going to make 8H2O out of that. And now we're doing pretty good. But we look up and our waters aren't balanced. We have 8 waters on that side and 4 waters on this side. So if we balance that out, 8 minus 4 is 4. Right? So what we're doing is we're doing 8H2O minus 4H2O. Right? And now that uses up all the H's on this side. And we have 4H2O. And that looks good. Now all we have to do is combine the reactions. Oh, I forgot to put the 5E minus. Sorry. 5E minus cancels out, so that doesn't have to come down. We have 4 waters, so that comes down. Plus MnO4, because it's not going anywhere. Plus, 5E canceled out. 5 Fe2 plus. 5 Fe3 plus. These 5s are getting kind of ridiculous now too. It's a racing 5. Plus Mn2 plus 8 OH minus. And if we're doing a base, we should have excess OH minus in the product because that's what makes it basic. If you end up with H plus over here in a basic solution, pretty much H plus anywhere in a basic solution, you haven't done it right. Throw in some OH somewhere, right? Try to make it look like you even understand the difference between acid and base, right? The concentration, the reason there's OH minus here is because there's unused base. That's what makes it basic. And base is OH minus. All right, so that should be it. Anyone with me at all? Oh, I got some thumbs. All right. So I'm blast. Nice work. No, 3, 6, probably. And then so that makes this 3, and this 2. And we're good?
If you told us that.
You made that look way too easy.
It is.
Is there like a trick for someone that doesn't find it easy?
Do a lot of them.
Do a lot of them till it's easy.
What about
Practice, drill.
You're missing the
I'm
dash
talking
in front of
about
aluminum, the whatever, what's in front of aluminum?
The male carbonate is
What?
What's in front of aluminum?
6-1.
What dash in front of
Not,
aluminum?
but I'm saying it's here, but you don't.
Oh, that's just for the number. That's for the number. So
I'm saying-
in something
I'm
like
saying
this,
you're
you put a 1 here.
Oh.
Yeah. Right. So yeah, that dash is just for the numbers. So these are the blanks. All right. Thank you, Maria. And then, so now we have this balanced chemical equation. And again, the way I do it, Brittany, right, is,
That the metal on the right.
well, it doesn't matter. If I go aluminum, aluminum here, right? There's 1 aluminum here, 2 aluminums there.
So that makes
So that doesn't balance, so I'm gonna put a 2 here. And remember, these numbers aren't permanent.
Yeah.
You can get rid of them anytime you want, but you have to go back to the beginning. You can't just leave 1 there and go, okay, that's good. So we have 2 here, 2 there. That's great. But now I have 6 nitrates. And over here I only have 1 nitrate. I can't split this up, so I have to put a 6 here. So now I have 6 nitrates and 6 ammoniums. I come over here, I have 2 ammoniums. So to get 6, I'm going to multiply 2 times 3. And then now I have 3 carbonates. I come over here and I have 3 carbonates. And you can do it with any of them. Right? That's why I don't break it down. If I recognize that I've got Al3 plus and CO3 2 minus on this side, oh wait, I'm breaking it up right now. Let's do it that way. So I have 6 of these. So when I break up this compound, the cation is NH4, and I have 2 times 3 of them, 6 NH4, and it's aqueous. I have 3 carbonates. You guys see that?
Yeah.
2 minus aqueous. I have 2 aluminum. Aluminum 3 plus aqueous plus 2 nitrate. Oh, 6.
6, yeah.
6 nitrates minus AQ. So that's the reactants. What's going on here? I have a vial of ammonium carbonate dissolved. I have a vial with water solubilizing aluminum nitrate. So I have 2 test tubes. This is my beaker diagram. And I pour them together. And I pour them together.
Uh-huh.
And I pour them together.
Yeah.
And they mix around in solution. I stir it up in my cauldron. And I make chants, right, to scare the locals. And then,
I can send this to you.
and so then they mix together. They do what we call a double displacement, which means I'm going to take the cation of the first one and put it with the anion of the second one. But right now I ignore these numbers here and focus only on the charge. So that would be, that's how I make this, right? That'd be the ammonium nitrate, 1 to 1. There's 6 of them. Here, aluminum's 3 plus, it goes with carbonate 2 minus. We do that crossover thing. If you can't remember how to do it, you just do that. And now we have our products. We look on the solubility chart. Carbonates, when mixed with aluminum, precipitate out. So that's our double displacement reaction. And since we did a double displacement reaction, that means all we have to do is take it apart. And so we just take them apart like we did here. And then this one's aqueous. This compound, ammonium nitrate, is aqueous. So we need 6 ammoniums because all nitrates are soluble. NO3 minus aqueous. And you can put brackets in if you want. I like to afterwards. And then when you make a product or a precipitate, it stays together for the total ionic equation. So when you break it up into all the ions that are in the solution, that's the total ionic equation. So as they're dissolved, you pour them together, they form a precipitate, they exchange cation and anion, and then some of it stays in solution sometimes. Sometimes they both come out, right? But not this time. This time only one thing came out. Now, to get the net ionic equation, that's just the reactant parts. So anything that's the same on one side, the reactant side, and it's the same on the product side, cancels out because they're still in solution in that beaker. Then we have 3CO2 here minus aqueous, oh that's CO3, sorry. 3 carbonates, aqueous, and it's AlCO2, aluminum carbonate on this side. So that's a change, right? It was CO3 in the aqueous condition, and now it's in the solid condition state. Then we look at, so carbonate stays, and then we look at aluminum. Aluminum's aqueous here and solid there. Change of state. Yeah, it went from California to Nebraska. And then we look at nitrate. Nitrate's the same on this side as it is on this side. So it's a spectator. And now this is the net ionic equation. Now let's use EQ. Here is the total ionic equation. And here is the molecular equation, or balanced. So this is the BME, the TIE, and the NIE, if you want to be like an acronym person. And you can make up cute little sayings about each one of these, if you wanted to, like I would. That's how I would do it. And then I wouldn't know what they meant, but I had this cute little saying playing over and over and over again in my head, which is why. So for me, learning is weird, probably different than you guys. I learn things as the concept they are. I don't try to compare it to something else, because it isn't something else. It's that. This is the net ionic equation. It's not like something that we already know. It's different than what we already know, and it's explained in a different way, and it means something else. So it's not like playing catch in my brain. Now in your brain, you might need to relate it to something you know and then make a change. But that's okay.
Catch and baseball are two different things, even though they both include catching ball. That's
Could
how
be.
you learn. They're two different
Yeah,
things.
like you could catch a fly, you can catch a fish, or you can catch a ball, but catching a ball is not like catching a fly, which isn't like catching a fish, to me. There are 3 different things. And yeah, catch is a similar word that ties them together, but in my mind, they're 3 different things that don't relate to each other. That's the way I think. I'm not telling you to think that way. I'm just saying I separate science from, physiology. Wait, physiology is science. But it's separate processes. I don't do that kind of relationship. So if you do, then you have to tell me so I can try to draw a parallel, because those parallels don't come to me, even though it's like part of teaching 101 or something. I don't know. So there we are. That's why I should have had to be forced to take a teaching class if I was going to teach at this level, because I teach at a college level, which you guys come in and you figure it out. That's what's supposed to be happening in education. I give you the tools, the equations, the ideas, and then you work on them until they're yours, right? But the tools are already mine. I'm sharing the tool set that I have and how to use those tools. It's up to you to spend the time trying to figure out how to do that. And especially as you move forward in your professional career, the more you take responsibility for the tools that are provided to you, the more reliable you are, the better offers you get, the more you separate yourself from your peers. And it's not about being better than them. It's not about, oh, I have knowledge and you don't. It's not about getting even with people who mistreated you. It's about bettering yourself, bettering the community, bettering society, and enjoying something, right? Well, the difference between when you started in high school and now is big, but between 20 and 30, it's huge. Between 30 and 60, it's gigantic, right? And then people start losing steps. And then it kind of we all pack back up together like we were in elementary school, where there's not really that many differences. We're just alive. But during that growth period, the difference between spending an hour doing something every day for the next 20 years and not doing it is going to make a huge difference. You can't make that difference up cramming. You can try, and most of us do try to do that. Oh God, I got 4 years worth of material to learn in thermodynamics, which is the change in energy when we do a reaction, because not all that happens is just the transfer of electrons. We transfer energy. Sometimes we go from a lower energy state to a higher energy state. Sometimes we go from a higher energy state to a lower energy state, and in between we give off energy. So we want to track that energy. And the basic principle that we use is just like matter is neither created nor destroyed, the total energy of the universe is constant, right? The total energy of the universe is constant, which means energy is neither created or destroyed. Uh-oh, it's a finite well. So the total energy of the universe is constant. So if we lose energy in one place, we gain it in another, right? So delta E, so we're going to say delta is the change, is change. Whenever you see delta, think change. Delta is the triangle. And so delta energy of the universe equals the delta energy of the system plus the surrounding. So we can break energies into we can break energies into individual universes, right? So each system is the reaction and the surroundings, and that entire thing is a universe. So we can limit the size of the universe, or we can make it bigger, depending on what we want to accomplish. But the overall change in energy is going to equal zero. So we have a plus and a minus. If we gain energy in one part, we lose energy in another. That's all that's saying. Internal energy, E, is often called U. What? E is often called U. So if you're looking for this in research, sometimes you'll see internal energy as E, sometimes you'll see it as U. It's the same thing. Changes to U can only be done by addition or loss of heat and work. So we either put work in, take work out, put in heat, or take out heat, right? And they're going to all balance out to the total energy. So Q is the work done on a system, and Q is positive. So if you do work on a system, the heat is positive. If work is done by a system, the heat is negative. Defining energy transfer. So that's what we're looking at. Energy transfer is energy transfer into the system or out of the system, into the surroundings or out of the surroundings. And then that defines the sign of the energy transfer. So we start at the initial state. If the energy total is less than the energy initial, right, then the delta change of energy is greater than zero. So if you have more energy, when you start with more energy and you end with less energy, the change of energy is positive, so energy goes to the surroundings. If the energy of the system increases, that means the initial energy is less than the final energy, then delta E is greater than zero. I said it backwards over here. This is less than zero. So if energy of the system decreases, this little sign here, when it's facing the zero, that means less than zero. When it's facing away from the zero, it means greater than zero. So energy in the initial state, when the system energy decreases, it's less than zero. When the system energy increases, it's greater than zero. Which means if we increase energy, if we go from a lower energy state to a higher energy state, delta E is greater than zero. If we go from a higher state to a lower state, then energy decreases. So we define delta U, change in U, or change in E, as the change of energy final minus the change of energy initial, which means energy of products minus the energy of reactants. So if delta U, or the internal energy of the system, is greater than 0, the system gains energy. If the energy is less than 0, the system loses energy. Okay. Sometimes a system transfers energy as heat only, not heat and work, just heat. So in that case, the change of energy is just Q. So the heat loss to the surroundings is less than 0. Energy lost is heat. So sometimes energy is heat and work, but sometimes work is 0. Sometimes the system doesn't do any work. Kind of like people who don't turn in their assignments. Their Q is high though. Lot of heat, not so much work. All right, so I think that's the devil's brigade, right? There's more. Never mind. I'll have to work on that one later. Heat lost by a system, Q is less than 0, exothermic. Heat gained by a system, Q greater than 0, endothermic. So remember, heat lost by a system, negative Q. Heat gained by a system, greater than Q. We already covered that the first time. A system transferring energy is work only. That means no heat's given off, we're just doing work. So this is a gas system. There's a piston here. We're driving that piston closed, forcing more energy into the system, and changing zinc plus hydrogen. What was that? All right. And then so you have energy initial, and it goes down in energy, so work is done on the surroundings. Okay. So work done by a system, work is what, less than 0. Work done on a system is greater than 0. Okay. So remember, if the work is being done by a system, that means it's what? We're doing what to the system, to the surroundings?
Heating up the surroundings?
Well, there's no heat. There's only work. So is the work? It's going to be negative. That's all. So if the work is done on a system, it's greater than 0. So positive means work was done on the system. So if you just see a number like 55, you know it's done on a system. It's work done on a system, and it'll have joules, right? Because joules is our. All right. So anyway, what is that? C8H18 octane, right? Which is a straight chain hydrocarbon that they add to gasoline to help burn at a higher temperature. Because if you burn at a lower temperature, you don't get as much energy out, and that's what happens. So some of it you lose as heat, some of it is lost as work. Okay. So your energy change is based on, this is combustion, right? And then we create water and CO2, but some energy is taking place. Because if you start with a higher energy and a longer chain, you're gonna give off energy. There's more energy in those bonds than there is in the smaller bonds. So it takes less energy. Energy's given off to break those bonds and form smaller bonds. So the key is whether just heat or heated work is produced, delta U is the same. The change in energy is composed of heat and work. If heat is 0, work is the entire change of energy. If heat is 0, then work is the entire change of energy, or any combination of the two. So you should get the signs of U, Q, and W correct, if nothing else, right? So for Q, plus means the system gains heat. So you add heat to the system, right? So when you're heating something, you're adding heat. It means the system loses heat. For W plus means work is done on the system. Minus means work is done by a system. So if you see the negative, work is done. If you see the negative, energy is lost. If you see the positive, energy is gained. You had to put energy into the system. An example, let's assign the relative signs for delta U, Q, and W of the system for the following process. An exploding grenade. Is energy given off? Is heat given off?
Yes.
So
Q is plus. Oh no, minus, it loses,
yeah.
It loses.
All right. So what about work?
Can you go back to the previous slide? I just kind of want to. Okay. Got it.
Yeah, and there should be a handout. Were you able to get the handout?
Yeah.
Okay. All right. So, here's the key. The grenade, this is not, slide did not go the way I wanted it to. All right, so let's just look. Oh, it did, I don't have it. Nice. Okay. So what happens to the, what happens with the grenade? Is work done by the system or on the system? So that makes it minus. Right? Let's go back.
Yeah.
Work done on a system. Work done by a system. That explosion is doing some work. And so delta U then is minus. All right, a melting ice cube, Q is plus, right? Change of state. And work is probably seems like we're going to have to figure that out. So the system is taking in energy, so work is done on the system. So the plus. So that means the change in energy is compressing a spring. No, U is, I did. That's a change in energy. So delta U, remember, U is E. Why? I don't know why I did this. I should have done this. Should have just left it all delta E.
Is U like Latin for something?
What?
Is the U like a Latin number or something? It's just U.
Aladdin.
No, that's
You rub the U and
Like
then it's
delta.
fine. And then it's sheep.
And then the G.
I think
Sheep.
he's saying Latin.
Latin.
Yeah.
Technically, it's Greek.
Or Greek.
Well, delta is Greek. But the U is I don't even know what it stands for. I'm sorry. Great question. I'll have to look it up now. I'll have to find out why they're using U for internal energy. Can't believe I don't know that. All right, so more nonlinear thinking. Q, W, U. So if Q is plus, W is plus, U is plus. If Q is minus, W is minus, U, delta, the change in energy is minus. However, you can have compressing a spring where work is done on the system, but heat is given off. So now you have a plus and a minus, and now it depends how much you compress that spring. So it could be a plus or a minus. Yes? Are you okay with that idea? That sometimes Q and W can be different, and then there's no change, and they could even be equal, and then there's no change in energy. So let's look at a system. Do I have this one? No, I don't have this one down either. All right, a system receives 785 joules of heat and does 1,050 joules of work. What is the change in internal energy for the system? Okay, so receives heat. So we come back here, receives heat. The system gains heat. So that's a positive number.
Yes.
And does 1,050 joules of work. The system, work done by the system. So the 1,050 is minus. Are you following me? 1,050 minus plus 785. So the overall work done is the combination of Q and W. Need a rolling black. This whole thing with the giant screen in the middle of the board. All right, so delta U, the change in energy, equals Q plus W. In this case, Q is 785.
Can't even see that.
Oh my lord.
Minus,
You're lucky I won't say my favorite battery.
265
I was.
joules.
yeah. Jules, is that right?
Yeah.
Oh, you weren't asking her. You were talking about the unit. All right. Fair enough. All right. So we're just going to add, that's what I'm saying. Q can be positive or negative, and so can W. But the total change in energy is the relationship between the two. That's all. And that'll help you do problem. Oh, wait, I have one more slide. in.
Yeah.
Yes.
-2.
My bad. All right.
My bad.
I didn't put it in there. I did the math wrong. All right, so the next slide is state functions. What are state functions? Oh, they only this would be a definition like for one of the words, if I don't make a list in the next week, state functions would be something to define on the test. A state function only depends on its current state, not how it got there. So it's what we say is a path independent. It's like if I walk to Maria this way, and here I am, hi Maria, and then I walk back, but then I walk to Maria like, it turns out that I'm in the same state when I get here. It doesn't matter how I get there. That's the difference between a state function and a function where it matters what the path is. So it's path independent. Examples of state functions. Delta T doesn't depend on how often you heat or cool the sample. It's going to be the change in temperature overall every time. So state function, change in temperature. Change in elevation doesn't depend on what route you take. For example, the elevation of Laramie minus the elevation of Cheyenne, someplace I spent like 5 years in a lab, in a box, doesn't depend on what route you take, right? If you start at 7,163 feet, which is over a mile in the air, by the way, because a mile is, I don't know, 5,280 feet or something. So well above Denver, in the Rocky Mountains, and then you go down to Cheyenne, which is 45, 50 minutes away on I-80 at 80 miles an hour, you drop 1,100 feet. No matter which way you go to get there. Like you can go down to Colorado, come back up and go to Cheyenne, and it's still the same change in temperature, so elevation, so it doesn't matter. So it turns out internal energy is also a state function, which is going to lead to some amazing things like the Hess cycle. So delta U, and we do it final minus initial, products minus reactants. And that determines the state. Finally, in order to do problem 1, we have to realize this relationship. Pressure and volume changes. Pressure stays the same, volume changes. P delta V, change in volume. Recall work equals a force times the distance. You probably don't know that. But work is force times distance. So how much force you use to go a certain distance. But it's also equal to P delta V. So force times height, change in height. So P delta V. So the pressure over a change in volume, which equals work done on the system minus P delta V. P delta V has the unusual energy units, liter atmospheres. So the energy conversion is 101.3 joules equals 1 liter atmosphere. But in order to solve, if you have 2 pressure changes, you need to change, if you have a pressure and a volume change, this is how you solve for work. And if it's work only, you don't have to add Q because Q is 0. If there's a Q, you add the Q to it to get the total change in energy. Here's an example. Burning gas in a cylinder releases 1,250 joules of heat. Releases heat, so that's Q minus, right? Release of heat. And the cylinder expands against an external pressure of 1 atmosphere. So the pressure's 1 atmosphere. And remember, liter atmospheres is the work. From a volume of 0.25 to 0.93. So the final volume is 0.93, initial volume 0.25. What is the change in internal energy for the gas in the cylinder? So we want to know delta U, or delta E as it's more properly represented here, which is Q plus minus P delta V, which substitutes for work. So Q plus minus P delta V. So 1,250 joules, right? That's what the heat that's given off, so it's minus. Plus the minus of 1 atmosphere times 0.93 minus 0.025 liters times the constant, right? The change, what is that called? What is that called? I just got done. There, the energy conversion to liter atmosphere units. 101.3, right? So now that's everything you need. 86.9 joules, not much energy compared to the heat part of this problem. This is very typical. generally heat is usually a bigger part of the transformation than work. So, yeah, go ahead.
Are we gonna get these constants on as like a printout?
Yeah, you can put that on your worksheet if I don't give it to you. It'll probably be on the last page of the test under useful functions, which I usually leave out. So that's all I wanted to do right now, and then we'll talk about stuff later.
Why was it a negative P delta V?
Because that's how it solves out. It's always negative P
Okay.
delta V. So if the change of volume, if the final volume is less, then we have a positive number. If the final volume is greater, it stays negative.
Okay.